Now for the moment you've all been waiting for, Lebesgue integration. All right, 4.2, Lebesgue integration of a bounded measurable function over a set of finite measure. So the real punchline there is everything that matters is bounded. We're going to develop this by going through several classes of functions. So what's going to happen is in sections 4.2 through 4.4, we develop Lebesgue integration of measurable functions. We'll do so for a class of functions, and then we'll use that class of functions to define the Lebesgue integral for the next and bigger class of functions. In this section, we'll start with simple functions. I'd call that class 0. This class stuff is all of my doing. It's not how the book describes it, but it's the protocol that the book uses. So we'll start with simple functions. We'll then use integrals of simple functions to define the Lebesgue integral of bounded measurable functions over sets of finite measure. So these are the functions of this section. Think of these as the class 1 functions. And what's going on, and it's fairly clear from the title of this section, we have everything with which we'll compute bounded. We'll compute using function values, and we've got bounded functions, and we'll compute using measures of sets, and we've got sets of finite measure. So maybe not everything is bounded. The sets themselves could be unbounded, but the measures of the sets are bounded. So the things with which we compute will be bounded, meaning there'll be no diverge to infinity or negative infinity type stuff when we deal with the integrals in this section. Later on, different story. In section 4.3, we'll consider non-negative functions. This would be the functions in what I'll call class 2. We'll define the Lebesgue integral of class 2 functions in terms of integrals of the class 1 functions. Now, we'll lose the boundedness stuff, but we'll be considering non-negative functions. So we might encounter unbounded integrals. We might encounter infinite integrals in that section. But one of the concerns is this infinity minus infinity situation. In Calculus 1, you had types of limits that were of an infinity minus infinity indeterminate form. And integrals are effectively limits, explicitly so in calculus, and in here limits approached in terms of soups and nths. But there'll be no infinity minus infinity concerns in class 2 because nothing's negative. So there's no subtraction, so there's no minus related. In section 4.4, we'll consider what are called integrable functions. And the definition of integrable in that setting is a little different. These will be functions that have a positive part and a negative part. By the way, the positive and negative part of a function will, maybe a bit surprisingly, both be non-negative. Even the negative part will be a non-negative function. So the positive and negative parts will fall into the previous class. And so we'll define integrals of these functions in section 4.4 in terms of integrals involving the previous class of functions. We will very much approach this by avoiding an infinity minus infinity situation. The integrable condition will require that the positive part have a finite integral and the negative part will have a finite integral. And then we'll just define the integral in terms of a difference of those two types of integrals. So we'll have finiteness when we ultimately do the subtraction. So very much of what we're doing in this chapter, later on at least, starting in section 4.4, will be an avoidance of an infinity minus infinity situation. Okay, now we just defined in the previous section Riemann integrals. Let's recall that real quick because we're going to mimic exactly what's done here in the Lebesgue setting. In section 4.1, we saw that we could define the Riemann integral of a bounded function on a closed and bounded interval in terms of lower and upper Riemann integrals, respectively, given here. What we did was we took the Riemann integral of a step function. Step functions are simple functions. They're simple functions defined on little intervals, where the functions are constant on little intervals. Simple functions are functions which are constant on measurable sets, and something about finite values. So we had defined Riemann integrals as integrals over phi, where phi is a step function. Phi is less than or equal to f. We take a sup, would produce a lower Riemann integral, lower because the functions phi are all less than or equal to f. Upper Riemann integral being an infimum of step functions where the step functions are greater than or equal to f, greater than or equal to upper Riemann integral. And of course, we said a function is Riemann integrable when those upper and lower Riemann integrals are equal to each other. So what we're going to do is follow a similar procedure when we develop Lebesgue integration, but instead of step functions, we're going to use simple functions. And that's about it. That's the big picture right there. Problem is that'll only work in this class 1 of functions, bounded functions on sets of finite measure, and we'll take it a little further than that later on. Hey, in calculus 1, you mostly deal with bounded functions on bounded intervals, and then you deal with improper integrals of this sort and that sort, where you integrate maybe over vertical asymptotes, or you integrate over infinite intervals. So it's developed in a similar way with what we'll do here. We'll expand this bounded stuff here in the next few sections, in other words. So we're totally doing what Riemann would do, with the exception that our simple functions, Lebesgue's simple functions, will play the role of Riemann's step functions. So first, we'll have to deal with the simple functions and what a Riemann integral of a simple function is. Simple function phi on a finite measure set E with canonical representation, psi, simple function psi, is a sum from I equals 1 to n of a sub I times a characteristic function on e sub I. That means being the canonical form means that the psi function only takes on the values a1 through a sub n and does so on the sets e1 through e sub n respectively. So the a sub i's are distinct and the e sub i's are disjoint. That's what canonical representation was. Then define the Lebesgue integral of psi over set E simply to be the sum from 1 to n of a sub I times a measure of e sub I. That's what I've been really tempted to call like a Lebesgue sum. We dealt with Riemann sums by drawing little rectangles. Okay, an alternative interpretation of those little rectangles is an integral of a step function. So here we've got an integral of simple functions. Well, I could think of these as kind of like Lebesgue sums. They're still, sort of like base times height. Height are the a sub i's, the y values, and the bases are measures of sets. I've been promising we were going to deal with Lebesgue integration using function values times measures of sets in a homage, I guess, to Riemann, an idea of Riemann sums and adding up areas of rectangles. Similar type thing here. One little comment. The reason we've dealt with this canonical representation is we could represent that simple function psi in some other ways. I need a well-defined definition of Lebesgue integral of such functions. So I need to have an unambiguous way to represent these simple functions. And the canonical representation is an unambiguous way. So that's the reason we've defined the integral of simple function psi using a canonical representation. Not that other representations wouldn't work. In fact, that's one of the first things we're going to address. So we've defined the Lebesgue integral in terms of a canonical representation. The next result will show us that the value of the Lebesgue integral of a simple function phi can be computed in a similar way in the event that the representation may not be the canonical representation. We mention this because, and we're going to need it in the first result we prove concerning Lebesgue integrals of simple functions. Lemma 4.1 says, let E sub I equals 1 to n be a finite disjoint collection of measurable subsets of a set of finite measure E. So disjoint right there is giving you a bit of information that we're about to use. For I between 1 and n, let A sub I be real numbers. Nobody said they were distinct this time. They were distinct when we had a canonical representation. If phi can be written as a sum from I equals 1 to n of A sub I characteristic function times E sub I on set E, then the integral of phi is the sum of the A sub i's times the measures. So the highlighted word there is kind of the new word. Maybe, no, I'm sorry. What's the new stuff is the fact that we haven't assumed the A sub i's are distinct. That's the new stuff. We do have the disjointness. We had that in the canonical representations too. But what we're saying is, well, the integrals are what you think they should be. If we have a sufficiently clean representation, though maybe not a canonical representation, that representation being we're dealing with disjoint E sub i's when we write the function like this. Let's go through proof. It's nothing surprising, but for completeness, let's go through this. Our first, very first result on Lebesgue integration. As given, let the E sub i's be disjoint and let phi be written like this. Okay, well, we got to get to the canonical representation, so we can use the definition of the integral of a simple function. So suppose lambda 1 through lambda sub m are the distinct values taken on by function phi. For 1 to m, define A sub j to be, and m was the number of values taken on, define A sub j to be the x values in E such that phi of x equals lambda sub j. All right, so what we're doing is basically something along the lines of, well, if A sub 1 and A sub 2 are the same, that's allowed in this setting, then we're taking set E sub 1, where the function takes on the value A sub 1, and the set E sub 2, where the function takes on the value A sub 1 as well. A sub 2 equals A sub 1. And we're gluing those two sets together. We're collecting those sets together. This is what we're doing. So on A sub j, then the function phi takes on the value lambda sub j throughout that set A sub j. That's how set A sub j is defined. All right, then we can take these A sub j's and lambda sub j's and produce a canonical representation of simple function phi as a sum from j equals 1 to m, lambda sub j, characteristic function on A sub j. That's a canonical representation. Well, if that's a canonical representation, then we can write the integral of that simple function phi in terms of that canonical representation, and here's what we get for the integral. Now, we need to show that is the same as what's given up here. Okay, so what we're going to do now is consider sets of indices. For j between 1 and m, remember 1 through m was the number of values the function takes on, let I sub j be the indexes I such that A sub I equals lambda sub j. For example, lambda sub 1 is a function value. I don't know, maybe these A sub i's here, maybe for every odd value of the index, these equal lambda sub 1, for all I know. Okay, then I sub j would consist of all odd indices I. Maybe A1, A3, and so forth. They all equal, say, lambda sub 1. That's allowable here. Then we're simply picking off the values of I for which A sub I equals lambda sub j. Then if we'll union all these I sub j's up, we get the total collection of indices I. Of course, that'd be a disjoint collection because the lambdas are distinct because they were related to a canonical representation of the simple function. All right. We have additivity of measures of functions. So if we take the measure of a sub j, we've actually written a sub j as a disjoint union of some of the e sub i's. That's how the indices were chosen. So we get that the measure of a sub j is the sum of the measures of the e sub i's when the index comes from capital I sub j. It's a lot of indices, but that's simply how we've partitioned up the e sub I pieces to create the a sub j's. So if we look at a sum from I equals 1 to n of a sub I times the measure of e sub I, that's the thing we're interested in, then we get the following. Hey, the measure of e sub I, when we sum those up over the I sub j values, sum over I an element of capital I sub j, a sub I measure of the e sub i's, then this sum over the I values produces the measure of a particular a sub j set. So we're about to use that. And we're letting j range from 1 to m here. J equals 1 to m, we're going through and finding where a sub j style, where the function takes on the value lambda 1, where the function takes on the value lambda 2 when j equals 2, and so forth, up through j equals m. So a range from 1 to m, because that's how many distinct values we have. Now, we know on this set, capital I sub j, the a sub i's equal lambda sub j, the a sub i's equal lambda sub j. That's what set capital I sub j was by definition. So I can replace over set I sub j, I can replace all of the a sub i's with a lambda sub j, and I can bring those out front, as we've done here. So we get a sum from j equals 1 to m of the lambda sub j's. That leaves you with sums of measures of e sub i's as given here. J equals 1, you get a sum over I sub 1. It's all the little e sub I things that make up a sub 1, for example. And that's why j ranges from 1 to m. As we observed upstairs, these things are precisely the measures of the a sub j's. There's the finite additivity part as explicitly applied here. So I can replace the second thing in square brackets with the measure of a sub j. And that is what we had as the definition of the integral over e of psi, because that's based on the canonical representation. So we can express the integral in terms of this summation, as well as the summation based on a canonical representation. The big key was to keep those sets you're dealing with disjoint and finite in this particular setting, finite in measure. All right, so this allows us to express integrals of simple functions even when the functions aren't given a canonical representation. They're not just given any old representation. We still have the disjointness on those sets, but they're given a representation that may not be the canonical one. Here's why we need that. All right, this ain't the last time we're going to see linearity and monotonicity of integration. In fact, we're going to see it a total of 4 times. Once for each of the classes of functions. I had class 0, 1, 2, and 3. Decided to call the simple functions class 0, demeaning their importance maybe in some sense. Yeah, I'm kind of thinking of them as just simply producing Lebesgue sums. But anyhow, we have 4 classes of functions, and for each of those classes of functions, we'll have a linearity and monotonicity result. And that result for simple functions says, let phi and psi be simple functions defined on a set of finite measure. By the way, all simple functions are bounded because they only take on a finite number of values. That was a definition of a simple function. The claim is for any alpha and beta, the integral of alpha phi plus beta psi equals alpha integral of phi plus beta integral of psi. In addition, this is the linearity result. The monotonicity result says if phi is less than or equal to psi on set E, then the integral of phi is less than or equal to the integral of psi. Okay, we've got to deal with something other than canonical representations. I got maybe one representation for phi, a canonical representation over a collection of sets, E sub i's. And I got a representation of psi over a different collection of finite sets. Well, I need a common collection of sets, and that's where the lemma will come in. Okay, so both phi and psi take on a finite number of values over set E, the set over which we're integrating. So we can choose a finite disjoint collection, E sub I equals 1 to n, say, of measurable subsets of E, where the unions of these E sub i's, disjoint union, so they're disjoint union equals set E, and phi and psi are both constant on each E sub I. So I'll have overlaps over where phi takes on the value A sub 1 and psi takes on the value B sub 1, say. Intersect those two sets, and that's how you're creating this collection of sets on which phi and psi agree. We need that so we can deal with the integrals of the sum. So let A sub I and B sub I denote values of phi and psi on set E sub I, where we've created the E sub i's, so we know they're both constant on those sets. The representations of phi and psi may not be the canonical ones. That's okay now that we've got lemma 4.1, but let the representations be phi equals a sum from 1 to n of A sub I characteristic function on E sub I, psi equals sum from 1 to n of B sub I characteristic function on E sub I. So here's your story. The E sub i's, they're disjoint, like we needed in that lemma. But maybe the A sub i's, maybe some of those are the same as each other. Maybe the A sub 1 is the same as A sub 5. So it's not a canonical representation necessarily. And same story over here. The sets are disjoint. Maybe these aren't distinct values. It's okay. Theorem 4.1 says you integrate them the way you think you should, by summing function values and measures of sets. Integral of phi, sum of A sub i's times measure of E sub i's. Integral of psi, sum of B sub i's times measures of E sub i's. All right, so now we've got summation representations for these integrals. So let's consider the simple function alpha phi plus beta psi. These take on, constant values on the sets E sub I. Those values are for this function. Takes on the value alpha A sub I plus beta B sub I on set E sub I. So we've got constant on the E sub i's for the sum as well. So lemma 4.1, the E sub i's being disjoint, tells us the integral of this function, that is the integral of this summation. So this is a representation of that linear combination in terms of characteristic functions, is the sum of the values times the measures on which the simple function takes on these values. Like a Lebesgue sum is where we are at this stage. Function values and measures of sets. Now, should be happy with this. Now we've got just numbers. Everything is a number here. The alphas are numbers, the A sub i's are numbers, the betas are numbers, the B sub i's are numbers, and this thing here, the measure of E sub I, those are numbers too. So we're going to use the impressive properties of distribution and associativity or commutativity and peel these apart. So you're in good shape now. You're just talking about numbers. So we get this summation. We can split up and bring the constants out. It's just distribution of real numbers. So we're in a familiar setting at this stage. That produces these two particular sums here. And we saw above, this is the integral of phi, and this is sum as the integral of psi. So there you go. The integral of the linear combination is a linear combination of the integrals. For monotonicity, suppose monotonicity of integral, right? I know we had monotonicity of measures in the past, and it's a similar idea, but the names are almost identical. I maybe try to be a little clear. We're talking monotonicity of the integral in this linearity and monotonicity results. Suppose phi is less than or equal to psi on set E. Define eta to be psi minus phi on set E. Then, by linearity, the integral of psi minus the integral of phi is the integral of psi minus phi. Integral of the linear combination is a linear combination of the integrals. And we've defined this thing to be eta. So this is the integral over E of eta. We're looking at having psi minus phi with psi greater than phi is a non-negative function. So we're integrating a non-negative simple function over some set, then that integral will be greater than or equal to 0. Psi is a simple function that's non-negative, so by definition, its integral will be a sum of measures times function values. Well, if function values are non-negative and so are the measures, so the integral will be non-negative as well. That is greater than or equal to 0. Rearrange this, and that produces the monotonicity claim. Take the integral of phi to the other side. You get the integral of psi is greater than or equal to the integral of phi as desired. So there's your first monotonicity result. So where we stand now is in pretty good shape as far as class 0 of functions goes. Class 0 being simple functions on sets of finite measure. All right, so now it's time to move on to class 1, and we'll define the Lebesgue integral for class 1 functions in terms of class 0 functions. We'll prove a monotonicity and linearity result for that class 1 of functions, and we'll wrap the section up by proving our first convergence theorem. So moving on to class 1, we're going to define lower and upper Lebesgue integrals for class 1 functions. We're totally doing the same thing that Riemann did, except we're using simple functions, whereas Riemann used step functions. So the definition is that f be a bounded function on a set of finite measure. Define the lower Lebesgue integral to be integral over phi, where phi is simple, and phi is less than or equal to function f. Take those integrals and then take a soup. We're taking lesser simple functions. So I expect the specific integrals to be, quote unquote, too small because we're taking lesser functions here. And then take a supremum, just like you did with step functions when you were dealing with lower Riemann integrals. And what'll come next will be the upper Lebesgue integral. How will that differ? We'll integrate psi is the symbol we use there. We'll integrate psi, where psi is simple and psi is greater than or equal to f. So then I'd expect specific integrals of those to be too big, so we'll shrink them with an nth, just like we did in Riemann integration. And indeed, we'll integrate psi is a simple function, greater than or equal to f, shrink them with an nth. The small ones you swell up with a soup. The two big ones you shrink down with an nth. This is still called a lower Lebesgue integral because we're still dealing with functions less than or equal to f in a limiting sense. There's your limiting sense right there when we did the soup thing, and down here where we did the nth thing. So lower and upper Lebesgue integrals, all right, short-term observation shouldn't be too surprising. When those are equal, we're going to say that function's Lebesgue integrable. Now we know monotonicity on the simple functions. So one thing we can immediately say is the lower Lebesgue integral and the upper Lebesgue integral in this class 1 of functions, these are finite, because we've got the monotonicity and the boundedness of the functions f. So all the simple functions will be bounded, and we'll get finite upper and lower integrals. Also, for any particular phi and psi, these phis are less, the phis are less than or equal to f, and the psi's are greater than or equal to f. So when I compare an integral of a phi to an integral of a psi, monotonicity of simple functions will tell us these integrals are less than those integrals. Not a big surprise, but that monotonicity will lead to the conclusion that lower Lebesgue integrals are less than or equal to upper Lebesgue integrals for the same function over the same set. Just a quick observation. It comes so easy given what we currently know. And so, bounded function f on a domain E of finite measure is said to be Lebesgue integrable over E, provided lower and upper Lebesgue integrals are the same. The common value is called the Lebesgue integral, denoted like this. It's very concise. As I mentioned before, we put a big ugly R out in front of integrals when they were Riemann integrals. Yeah, we were saving the cool notation for Lebesgue integrals. No dx stuff. And it's tradition just not to put any of that x dx stuff. You're integrating a function over an interval. We're not going to do u substitution or anything like that. We're building a body of knowledge, a theory of Lebesgue integration, ultimately. So there's what Lebesgue integrable means and what the Lebesgue integral is, but in a very limited sense. For measurable functions, bounded measurable functions on sets of finite measure for class 1 functions. So we got it defined. I wonder how it behaves. I wonder if we've got linearity and monotonicity of these as well. Yeah, you do. How are you going to prove it? Probably going to depend on the fact that we got linearity and monotonicity for simple functions, and these integrals are defined in terms of simple functions. We'll see below that this works in the sense that all class 1 functions are Lebesgue integrable. One reason this is happening is the fact that we were considering measurable functions. Back in chapter 3, I tried to inspire the idea that, yeah, I mean, this definition of measurable function is the weirdest thing. Let's think about how we're going to use them. And then it was going to be used in terms of Lebesgue integrals and how we would approach that in terms of kind of like Lebesgue sums, which you now know what we mean by that. It's the definition of measurable function really that's making this tick, and it's worked so well because we've cleverly chosen what it means for a function to be measurable. But we'll see that all these class 1 functions are Lebesgue measurable here in just a second. Theorem 4.4 from this section. But a quick observation while we're in a neighborhood. So we've gotten as far right now with the Lebesgue definitions as Riemann goes, in calculus 1 at least, for bounded functions on closed and bounded intervals is how Riemann starts. Well, we should be able to agree on some things with Riemann then. Recall from the Riemann-Lebesgue theorem, a link to the notes given there, a bounded function on interval AB is Riemann integrable if and only if that function f is continuous almost everywhere. So continuous almost everywhere in this setting means Riemann integrable. Okay, continuous almost everywhere means measurable, right? I think I've mentioned this in passing, but here's all the details on that, right? Proposition 3.3 says a real valued function that's continuous on its measurable domain is a measurable function. So continuous functions are measurable. Proposition 3.5 part 1 says if f is measurable on a set and f equals g almost everywhere on that set, then g is measurable. So I can take continuous implies measurable and continuous almost everywhere, so I'm doing an almost everywhere thing, to conclude that functions which are continuous almost everywhere, those must be measurable as well. So we found common ground between a bounded function that's continuous almost everywhere, to which we can apply Riemann integration, and the fact that's a class 1 function shows us that we can talk about the Lebesgue integral as well. So in this common ground, I expect these two folks to get along. I expect the Riemann integral and the Lebesgue integral to be equal. We just needed to make sure we had the kinds of functions on which these two approaches to integration are defined. And theorem 4.3 says, let f be a bounded function defined on closed and bounded interval ab. If f is Riemann integrable over ab, then it's Lebesgue integrable over ab, and the two integrals are equal. Okay, so in the common ground, when Riemann integration is defined, then Lebesgue integration is defined, and we get the same values out. Okay, the proof is actually just one slide. It's a quick one. And here's what we get. It's simply a matter of comparing soups and nths with a little observation that step functions are simple functions. Step functions are examples of simple functions. There's plenty of simple functions that aren't step functions. Step functions are constant on intervals. Simple functions are constant on measurable sets. Well, intervals are measurable sets, but not all measurable sets certainly are. Not all measurable sets are intervals. So the collection of step functions is a proper subset of the collection of simple functions, if you like. Okay, so suppose we have Riemann integrability. All right, then let's look at the lower Riemann integral. The lower Riemann integral is defined as a sup over all step functions less than or equal to f, integral of those step functions. So we're taking a sup over all step functions of these integrals. Let's look at a bigger collection of functions. Let's go from step functions to simple functions. Suppose we took a sup over all phi less than or equal to f, where phi is a simple function, integral of phi. Greater than or equal to, think of it like this. Every one of these step functions over here is included in this collection of simple functions over here. But there's maybe more simple functions. So over here, we're taking a sup over a little set. Over here, we're taking a sup over a bigger set that includes all the stuff in that littler set. We're taking a sup over a bigger set. Well, bigger sets can have bigger things in them, and so their sups are bigger. So property of suprema, we're taking a sup of a collection of real numbers here. These are definite integrals, so they're actually just real numbers. The sup over here, all those real numbers are included over here and more. Well, then the sup will be bigger. If it helps you to analyze this at this level, you should be able to handle the sup arguments. But if you think about maximums, that's not totally legitimate, but it's not a bad way to remember how it works. Hey, the maximum over a little set is less than or equal to the maximum over a set that includes that little set and more. Yeah, this could have more big stuff in it. Property of sups. Hey, wait a second. The sup over all simple phi less than or equal to f of these integrals, that's the lower Lebesgue integral. How you notice a Lebesgue integral? I put the set down here over which we're integrating, and I didn't put all the r stuff or the x dx stuff like we're doing with Riemann. So this is the definition of the lower Lebesgue integral. We observed above, lower Lebesgue integrals are less than or equal to upper Lebesgue integrals. Ultimately, it's based on monotonicity of the integral for simple functions, but we got that inequality. We shifted over to upper Lebesgue integrals. That was defined as an nth over all psi greater than or equal to f, integrals of psi. Now using simple functions, greater than f, giving me integrals that are too big, and shrinking it with an nth, shrinking it with an infimum. Well, suppose we look at now the transition from simple functions to step functions again. Suppose we took an nth over all capital S greater than or equal to f, where capital S is a step function, and we'll integrate those. All right. It's the same argument we had up here, except now we're doing nths instead of sups. So let's see, we had every number in this set based on a step function is also a number in this set based on a simple function, because step functions are simple functions. But there could be more stuff, more numbers in this set. So when I take an nth of a larger set, we get smaller stuff potentially. I definitely get something less than or equal to the nth over here. Think of it as sets with a few real numbers in them. I choose the minimum versus a set with those same numbers and some more. Well, is it going to have a smaller minimum? No, these aren't really mins. These are nths, property of infinite. So we get this relationship, and the inequality goes in this direction this time because we're looking at nths instead of sups. And the infimum over all step functions greater than or equal to f. Why, that's the upper Riemann integral by definition. So we've got the lower Riemann integral less than or equal to upper Riemann integral. But wait, we hypothesized that this function was Riemann integrable. Well, if it's Riemann integrable, then these outer things are all the same. Okay, then all the inner things are the same as well. So all these inequalities actually must be equalities, knowing the outer things are equal to each other. The inequalities must be equalities. And so, hey, the lower Lebesgue integral equals the upper Lebesgue integral. That's the very definition of Lebesgue integrable. And we've got equality between that value and all these other things. That is, the value of the Lebesgue integral is the same as the value of the Riemann integral. That's a cute little result. It's really ultimately just based on properties of sups and nths. So kind of like that. Back to the notes. Next result says, maybe a little soapbox statement about Theorem 4.3. We must be on the right track. We got Lebesgue agreeing with Riemann as they were supposed to do when they're both defined. We need to make sure we get a clean body of knowledge out of this, a neat theory. I want to be able to integrate more stuff, for one thing, and I want to have a nice theory of integration. Right now, the only thing we've looked at is linearity and monotonicity. We'll look at it again for this class of functions, class 1 functions versus just the class 0 simple functions. And as observed above, we've claimed that if f is a bounded measurable function on a set of finite measures, it really is integrable with the definitions we've given. That is, all class 1 functions are integrable. Integrable really wasn't an issue with simple functions. We had the definition and that was pretty much it. Here, we've done upper and lower Lebesgue integrals, so there's a little bit to show. So let's look at a proof of that. Okay, all class 1 functions are integrable. That is, the upper Lebesgue integral equals the lower Lebesgue integral. Okay, I'm going to use a little bit of knowledge from our past, chapter 3, the simple approximation lemma. Let n be a natural number. The simple approximation lemma said, for any epsilon greater than 0, take epsilon to be 1 over n, there's simple functions, phi sub n and psi sub n on set E, for which f is sandwiched between those two simple functions. And the two simple functions are within epsilon of each other. Simple approximation lemma. You can get close to a measurable function with a simple function. The simple approximation theorem we considered as a sequence of functions that approached. And here we're also creating phi sub n's and psi sub n's. So we are creating a sequence on this as well, based on this natural number n. So for epsilon equals 1 over n, such phi and psi exist. It's a simple approximation lemma. By monotonicity and linearity for simple functions, we know, let's see, phi sub n minus psi sub n is greater than or equal to 0. So that tells you, maybe here's the place to observe, phi sub n is less than or equal to psi sub n. So we know that we get a monotonicity behavior when we compare the integrals of those two. That is, 0 is less than the integral of psi sub n minus the integral of phi sub n. This integral is less than or equal to that integral take that inequality and rearrange it. It produces this first little inequality. So there's the monotonicity part for simple functions, the only monotonicity we have so far. Here we've got a difference of integrals. The linearity part of proposition 4.2 allows you to write that as an integral of the differences. Linear combination of integrals is the integral to the linear combinations. So we get an integral of psi sub n minus phi sub n. And monotonicity, again, we know that psi sub n minus phi sub n is bounded above by 1 over n. Right, we've got this kind of bounding here. View this as an integral of the simple function that's a constant of 1 over n on set E. It's a simple function, and this is its integral. So we're using monotonicity of the integral of simple functions there again, comparing this simple function to this constant simple function that takes on the value 1 over n. So we've got the psi sub n minus phi sub n bounded by this. Not a surprise, you get 1 over n times the measure of the set as, as an upper bound. Okay, now we want to talk about upper and lower Riemann integrals. Those are, Lebesgue integrals, upper and lower Lebesgue integrals. We know that the upper Lebesgue integral is greater than the lower Lebesgue integral, an observation from above based on simple functions, it turns out. So we get 0 is less than or equal to this difference. This one is bigger than that one, as observed earlier. The upper Riemann integral is exactly this. It's an inf over integrals of simple function psi, where psi is greater than or equal to f, greater than or equal to, right, upper Lebesgue integral. From that, we're subtracting an integral of simple functions phi, where phi is less than or equal to f. Right, phi less than or equal to f, giving a lower Lebesgue integral, even when we take a soup. Okay, now I want to pick these particular phi sub n, psi sub n's, satisfying these conditions we were talking about upstairs. This whole thing started with n as a natural number. And, you know, we're dealing with epsilon equals 1 over n in the argument to come. But we've created for this n value these psi and phi simple functions. Okay, so think of it like this. I'm going to choose, we're taking an inf of a set. In this set bracket, there's a bunch of numbers. Okay, they're numbers that were generated by integrating particular kinds of simple functions, which are just taking an inf of a set of numbers. When I say pick psi sub n and the integral over e of psi sub n, that's one of the numbers in this set. Well, you've taken an inf over this set of numbers. The inf is less than or equal to one of the numbers in that set. Inf behaves, you know, in that sense like a min. There may not be a min because it could be an infinite set, but we get choosing a particular element of this set that is in particular one based on simple function psi sub n. Psi sub n really is greater than or equal to f, right? Yeah, there it is. Psi sub n is greater than or equal to f. So I picked a particular element of that. This is an inf. We'll get something bigger, and there's the greater than or equal to on that. How about I choose a phi sub n? One of these. So it's a number in this set effectively. We got phi sub n less than or equal to f. There it is right there. Okay, here we were taking a soup of this collection of numbers, and we've chosen a particular number in that set. Well, a soup is greater than or equal to one of the elements of this set. Greater than or equal to, oh, wait, there's a negative sign out front. So the soup is greater than or equal to an element of the set. So the negative of the soup is less than or equal to the negative of some element of the set. So we're good on the inequality. The negative sign saved us in the soup setting. Now we've got the integral of psi sub n minus the integral of phi sub n. And we saw upstairs that that integral, that difference of integrals, is less than or equal to 1 over n times the measure of e. And you can do this for any natural number n. That is, you can find the psi sub n's and phi sub n's that satisfy this. Okay. We know the measure of E is finite. set of finite measure, because we're dealing with, class 1 of functions. We've got 0 is less than or equal to the upper Lebesgue integral minus the lower Lebesgue integral. We've got that less than or equal to 1 over n times the measure of e for an arbitrary n, and the measure of e is finite. N can be anything, so make n sufficiently large. This can be made as small as you want, and so I can draw the conclusion that this thing here is less than or equal to 0. We already had it bounded below by 0. These must be equal to each other. That is, the upper Lebesgue integral and the lower Lebesgue integral must be the same, which is the very definition of Lebesgue integrable. So it worked. The definition we're using is valid for all class 1 functions. All class 1 functions are Lebesgue integrable. Turns out, we'll see somewhere in chapter 5, the converse of theorem 4.4 also holds. If bounded function f on set of finite measure e is integrable, that is, if the integral exists, then it turns out that must be a measurable function. To be explored in touch more detail in section 5.3. Let's leave it at that. All right, linearity and monotonicity. Let's do linearity and monotonicity for class 1 functions. Proposition 4.2 was linearity and monotonicity for simple functions, class 0 functions. Okay, well, let's prove it for class 1 functions. Linearity and monotonicity says virtually the same thing, except for the setting. You're going to see linearity and monotonicity 2 more times after this because we got 2 more classes of functions to go. Hypotheses are let f and g be what I would call class 1 functions, bounded measurable functions on a set of finite measure e. Then, for real numbers alpha and beta, the integral over e of the linear combination is the linear combination of the integrals. That's the linearity part. And if f is less than or equal to g on e, then the integral of f is less than or equal to the integral of g. That's the monotonicity of the integral part. Let's look at a proof of that. All right. Theorem 4.4 tells you, hey, alpha f plus beta g, these really are integrable, because if f is a class 1 function and g is a class 1 function, then so is a linear combination. This thing here is bounded, a bounded function, and said e has finite measure. Okay, so for the proof, we'll go through a handful of steps. If phi is simple, then for non-zero alpha, alpha times phi is also simple. Just the values of it change. It still takes on a finite number of values and on the same sets. If alpha is greater than 0, we're defining these things in terms of imps and sups. So the sign of the coefficient will affect things. The integral over e of alpha of f, by definition, would be the inf over psi greater than or equal to that function, alpha f, the integrand. Right? I'm taking simple functions greater than or equal to the integrand, and we're integrating those simple functions. I got to put set brackets around it to be consistent with what we had before, but it's understood here. We got a set of values, and the size, these are simple functions, right? Simple functions. So same thing we have by definition. I can rewrite that as given here. All I've done is taken the little inequality and divided both sides by alpha. So now we get psi divided by alpha greater than or equal to f. Same thing, same collection of numbers. You can do that because alpha is greater than 0. So no division by 0, no reversal of negative signs. And this we can write as, I'm going to put an alpha outside and an alpha inside. All right, I can move that alpha inside that inf, property of infs, since it's positive. Then I could take the alpha inside the integral. That's actually linearity of the simple functions, and then we could get the cancellation there. So we have equality between these two things here. and taking the inf of some function greater than or equal to f, some simple function greater than or equal to f, integrals of these simple functions, that is the integral over e of f. So it's a kind of funky way that we got the constant alpha outside the integral, but we went to imps and we fiddled around with some paperwork in the middle to keep the books balanced and got the alpha outside in that manipulation. What if alpha is negative? Well, do the same thing, but let's see, when we do the division, that'll reverse some inequalities. When we take the alpha in and out of the inf, that'll affect some things as well if alpha is negative. Inf of a set of numbers, when we multiply all those numbers by negative, some things change. Explicitly this. All right, suppose alpha is negative. Integral over e of alpha f, same way we started the other one. All right, now I'm going to divide both sides by alpha in this little inequality. But alpha is negative, that reverses the inequality, giving us phi divided by alpha is less than or equal to f. We've done the division. Okay, that's all we've done from here to here. This is the inf of, same thing, taking an alpha outside the integral and an alpha inside the integral. Can't argue with that. Linearity would let me take the alpha inside and cancel the alphas. So no problem there. Now I'm going to bring the alpha outside the inf, but it's negative. How do negative numbers affect orderings and inequalities? Greater thans become less thans. So bringing that alpha outside that set, the inf gets replaced with a sup. It's properties of ints and sups when you multiply elements of those sets by a negative. But it should seem quite plausible to you at the very least. Hey, negative numbers reverse inequalities. So the infs become sups. So we got the alpha outside. The inf has become a sup. Oh, that works out really well because we had functions less than or equal to f. We got functions less than or equal to f. I want to be taking a sup to associate it with Lebesgue integrals. And that's exactly what we have here. Here we've got a sup of simple function less than or equal to f, integral of that simple function over all such simple functions. That's the definition of the, let's see, sup. That's a definition of the lower Lebesgue integral. But f itself is Lebesgue integrable. So we get the, as we saw upstairs, so we actually get not the upper or lower Lebesgue integral, we get the common value of the Lebesgue integral. So this produces the Lebesgue integral and we got the alpha outside. So it's just a matter of changing settings to where you can move the alphas around. Where do you know you can move the alphas around? When dealing with simple functions. We showed that with linearity in the simple function setting. Okay, so far so good. We can bring alphas outside when they're positive or negative, and of course when they're zero, the integrals are all zero, so easy enough on that one. So that takes care of what I'd kind of call a scalar multiple part of this. If we were in a vector space, I certainly would call it scalar multiples, but we can bring alphas, constants outside of integrals. How about the function addition stuff, what I'd call vector addition, if we were doing something in vector spaces? So to complete it, we'll take alpha and beta equal to 1 and deal with the sum f plus g. I combine the result for f plus g and the result for scalar multiples, constant multiples, and then we get the linearity that was claimed. Okay, so we'll look at f plus g in this case, treating the alpha and beta as 1. Let psi1 and psi2 be simple functions for which f is less than or equal to psi1 and g is less than or equal to psi2 on set E. Then the sum, psi1 plus psi2, is simple. Sum of simple functions is simple. All simple was measurable and takes on a finite number of values. I'm sure sums of simple functions are simple. The inequality behaves the way it should. F plus g is less than or equal to psi1 plus psi2 on set E. So, dealing with let's see, what are we using here from proposition 2.2? That was linearity and monotonicity for simple functions. Let's see, we'll take the integral over e of f plus g. That'd be the nth over all phi greater than or equal to f plus g integral over e of phi. Definition of integral of class 1 function f plus g in terms of simple functions. Okay, we've got this less than or equal to psi 1 plus psi 2. All right, let's see, that comes from, this is pretty subtle, choosing a particular simple function that's greater than or equal to f plus g. Here we've taken an nth over all simple functions greater than or equal to f plus g, an nth, like a min. And here we've taken a particular one. Well, if this is the nth, then a particular one will be greater than or equal to that. So psi 1 plus psi 2 is indeed a simple function greater than or equal to f plus g. So it's one of these phis in this whole collection of all such simple functions phi greater than or equal to f plus g. Here we had an nth. Okay, so the inequality here actually comes from properties of infima. 4.2 gave us linearity, so here comes the 4.2 stuff. Integral of the sum is the sum of the integrals. And we've just seen then that the integral over e of f plus g is less than or equal to the sum of the integrals of these phis and these psi's. And this holds for all simple functions. Psi 1 and psi, and phis and psi, sorry, psi 1 and psi 2. So this holds for all simple functions where we get this inequality here. Simple functions greater than or equal to the corresponding measurable functions. Okay, then integral over e of f plus g would be less than or equal to the nth over all psi 2 greater than or equal to g, nth all psi 1 greater than or equal to f, linear combination. Okay, we just established the inequality with those integrals up here. Integral of f plus g less than or equal to integral of the sums, or sum of the integrals by the linearity. Now we're going to take a couple of nths. Inequality is still preserved. Nth over all psi 2, nth over all psi 1. We'll do them one at a time. If memory serves, the book skips some of these steps. So it's inserted to make it a touch clearer. Take an nth over psi 1, that's a constant, and that becomes an integral. That becomes a Lebesgue integral over e of f. Actually, it becomes what? An upper Lebesgue integral, but we've assumed Lebesgue integrability on function f. So we get a Lebesgue integral here. Take the nth over the psi 2's, and this second one turns into an integral here. And we've got the integral of f plus g is less than or equal to the sum of the integrals. But we're supposed to get equality. Okay, so we're only halfway there for this linearity part. We got to reverse the inequality. Okay, so choose some phi 1's and phi 2's. Let these be simple and less than or equal to f and g respectively on set e. Then the sum, which is simple, is less than or equal to f plus g, and quite similar to what we just did. Integrate f plus g. That by definition, so here's a definition in terms of lower Lebesgue integrals, is a soup over psi less than or equal to f plus g integrals of psi. I could use a phi there, I suppose. We've chosen a particular one of those simple functions, the simple function phi 1 plus phi 2. This single simple function, which is simple and less than or equal to f plus g, so it's one of these things here. And usual story, this was a soup, so it's greater than or equal to one of the particular elements of that collection. Using linearity here, this is a linearity applied to the simple functions, phi 1 and phi 2. And then we'll take soups over all such phi 1 and phi 2, kind of like we did in the previous section. And that produces integrals. We've got the inequality reversed, and we can draw the conclusion of equality. So let's see, we've got this, the integral of the sum equal to the sum of the integrals, right? We got the constant multiple thing. Oh, the monotonicity thing, that's what's left. So we've established this part in pieces. Think of this as a linear combination of two vectors. We took care of first the scalar multiplication, And second, the vector addition. Okay, they're not vectors, but think of it like that, and it's consistent with your experience from linear algebra. For monotonicity, suppose f is less than or equal to g. Okay, if we take the integral of the difference, that's the difference of the integrals, because that's linearity that we've already established in the first part. You know, g minus f is greater than or equal to 0. That's what assuming f less than or equal to g on set E implies. So when we integrate this, we could compare this, say, to a simple function, phi, which is a 0 function. I know when I take any simple function less than or equal to g minus f, like the 0 function, we can make this comparison because I know we've got monotonicity in terms of simple functions, and this integral would be defined in terms of simple functions. So we get the integral of the difference is greater than or equal to 0. The integral of the difference is the difference of the integrals. So we've got this greater than or equal to 0, rearrange it, and it produces the monotonicity result. So linearity and monotonicity, part 2. For our second class of functions. We got 2 more classes of functions to go. We got 2 more linearity and monotonicity theorems to introduce. Okay, we can use the linearity and monotonicity to prove a couple of quick things here. Let's just go straight to the proofs for the statements of these. Corollary 4.6 says that f be a bounded measurable function on a set of finite measure. Yeah, of course, it's got to be what I've called a class 1 function. Suppose A and B are measurable disjoint subsets of E. Then the claim is the integral over those disjoint sets of f equals the integral over A of f plus the integral over B of f. It's kind of an additivity style thing. You called it additivity when you had similar behavior for Riemann integrals in Calculus 1. So this is an additivity of sorts. We're going to have to appeal to one of the homework exercises to get all the details in this one, but let's throw some characteristic functions around. Consider f times a characteristic function on set A and f times a characteristic function on set B. First off, these are bounded functions. All we did was make the function 0 in certain places. These are also measurable functions, so we could get that from the definition of measurable. A and B are disjoint, so when we take f times a characteristic function on the union of A and B, we can write that as f times a characteristic function on A plus f times a characteristic function on B because of the disjointness. So what's going to happen here is, hey, this just picks off the values of f on set A and gives us 0 everywhere else. This just picks off the value of f on set B and gives us 0 everywhere. So when I add these together, if we're off of A, set A, and set B, if we're not on A union B, those particular input values, it gives out 0, right, like it should. If we're on set A, take an x value on set A, you produce this plus 0. You're on set B, you get the function value on set B plus 0. So you do get the equality there. It's a neat little way to take a particular function and write it as a sum of 2 functions. You like sums of functions, don't you? Because you got linearity under your belt from the previous result, the previous theorem. Problem 4.10 says for measurable subset E of set E, the integral over a measurable subset E1 of a set E, the integral over E1 of f is the integral over E of f times a characteristic function. So a little bit of work, heavy lifting being done in this one by problem 4.10 allows us to associate integrals over subsets using characteristic functions, which is exactly what we need for this. So now we can take these integrals and relate them to these functions. So the integral over A union B of f is the same as, by that exercise, the integral over E of f times a characteristic function on that set. Exactly what this says here. The E1 set is A union B in this little statement here. So I'm using problem 4.10 on this part. Hey, f times the characteristic function on A union B, we can write that as a sum of these two functions. So let's make a substitution there. Now we're business. We got an integral of a sum. That's the sum of the integrals. So says theorem 4.5, linearity on this class of functions, class 1 of functions. And using the exercise again, problem 410, hey, the integral over e of f times the characteristic function on A, by that exercise, this is the integral over a of f. Similarly, the second one is the integral over b of f, and that was the claim. Integral over a union b of f is the integral over a of f plus the integral over b of f, assuming a and b are disjoint. If they ain't disjoint, then a lot of this falls apart. Another corollary says that f be a bounded measurable function on a set of finite measure. The absolute value of the integral is less than or equal to the integral of the absolute value. Something you see in Calculus 1. Given my area, it's something I more often deal with in the complex analysis. Similar result holds in complex. We don't use absolute values. We use modulus in the complex setting, but similar result holds. All right. First off, the absolute value of f is measurable when f is. Proposition 3.7 guarantees that. Something about compositions of measurable functions are measurable. There's a bit of hypotheses on that, but we observed at the time in the notes that the implication was if f is measurable, the absolute value of f is measurable. If f is bounded, certainly the absolute value of f is bounded. We know negative absolute value of f is less than f is less than or equal to absolute value of f point-wise. They say onset e, so at all points of e. And we've got linearity and monotonicity. So we'll just integrate each of the three. That preserves the inequality. We can bring the negative sign out in front of that first integral. That's linearity, the constant multiple part. Constants come out front. And then we can say, hey, you got this integral over e of f bounded above by the integral of the absolute value of f over e, and bounded below by the negative of that same quantity. That is the absolute value of the center part is less than or equal to the positive side. That's high school algebra there on what inequalities mean as they relate to absolute values. So we've got this bound on absolute values of integrals as well. And all this coming out of linearity and monotonicity for class 1 of functions. Okay, we're almost there. What we're going to look at now is related to sequences of functions. I'm going to consider a sequence of functions and try to see when I can take limits in and out of Riemann integrals, or ultimately Lebesgue integrals. Recall a sequence f sub n of Riemann integrable functions on the interval a, b, which converges uniformly to function f on a, b, satisfies the following. We even mentioned this as motivation for a new kind of integral. When you've got uniform convergence of the sequence f sub n to function f, sequence f sub n approaches f pointwise, uniformly, more than pointwise, then the limit of the Riemann integrals is the Riemann integral of the limit. When you got uniform convergence in Riemann integrals, you can take that limit inside these integrals. It was outside the integral, now it's inside the integral. You got uniform convergence, you can do that. You ain't got uniform convergence, you can't do that. We'll even have some trouble with it in the Lebesgue setting. So you can take limits in and out of integrals when you get the right kind of convergence. For Riemann, it's uniform convergence. Guess what? If you've got uniform convergence in the Lebesgue setting, it's going to work as well. You can take limits in and out of integrals. So this following result we will use at times, but having uniform convergence we want weaker conditions than that to take limits in and out of integrals. But as a first step in that direction in the Lebesgue setting, that f sub n be a sequence of bounded measurable functions on a set of finite measure, E. So f sub n is a sequence of class 1 functions. If f sub n approaches f uniformly on E, so function f is a uniform limit of this sequence of functions throughout set E, then the limit of the integrals of the f sub n's is the integral of the limit. That is, it's the integral of the f function. So you can take limits in and out of integrals in the Lebesgue setting for class 1 functions when you have a uniform convergence. We can do better than that, but we're starting there. Theorem 4.8. Okay, there's a statement. All right. Convergence is uniform, and each of the f sub n's is bounded. Bounded measurable functions. The limit function must be bounded as well. Sequence of bounded measurable functions, we've got that bound. If we choose n to be a natural number and any epsilon greater than 0, we can get the absolute value of f sub n minus f to be less than epsilon on that set. So that gives us the boundedness of the f sub n's based on the boundedness of the function f. F is a pointwise limit of a sequence of measurable functions. So it itself is measurable. That was theorem 3.9. Pointwise limits of measurable functions are measurable. So let epsilon be greater than 0. Choose a capital N. We know this can be made small. So make this less than the epsilon divided by the measure of E. Based on the uniform convergence, this can be done. So for the uniform convergence, I can make throughout set E, on set E, that's what we were doing up here. On set E, I can make f minus f sub n less than epsilon over the measure of E. So make it less than something throughout the set, make it less than epsilon over the measure of E. This will eventually hold, that is, for all indices greater than or equal to capital N. That's the definition of uniform convergence of a sequence of functions on a set. You see the for all x that you're used to seeing from uniform convergence from senior level analysis? Yeah, when they say on set E, they're doing the for all x thing right there. So definition of uniform convergence. All right. So if we look at the integral over E of f minus the integral over E of f sub n, we get the following. Difference of the integrals, right, we're trying to make that less than epsilon, so we're going on this. Difference of the integrals be the integral of the difference. That's linearity. Corollary 4.7 allowed us, we get the absolute value on the outside. We can take that absolute value on the inside. Hey, we've got that integrand bounded above by epsilon over the measure of E on set E. Absolute value of f minus f sub n, that's less than epsilon over the measure of E. That's what we were doing on the previous slide using the uniform convergence. So the uniform convergence big time is used right there. So it should have a strict inequality here, the way we had that bound set up previously. And then we'll multiply that by the measure of the set. And what we're doing is a monotonicity type thing, if you like, here as well. But we've got a bound on the integrand. I guess actually, yeah, we got a bound on the integrand and the measure of the set. The measures cancel, we're left with an epsilon. We just showed that when n is sufficiently large, the capital N given on the previous slide, we get the absolute value of this minus this sequence term to be less than epsilon. So we can draw the conclusion that the limit as n approaches infinity of this sequences approaches that number. These are numbers because they're definite integrals. So we're really dealing with a limit of a sequence of numbers and what's said here. But I want to do better than just straight up uniform convergence. We're in general, we're interested in when we can take the limit outside integrals. When is it that the integral over e of f equals the integral over e of a limit of a sequence, where f is the limit of a sequence, equals a limit of the integrals? When can you take limits outside of integrals like that in the setting of a sequence of functions f sub n converging to a function f? Well, when you've got uniform convergence, you can do that in the Riemann setting for the appropriate kind of functions, and in the Lebesgue setting. We just proved you could when you have uniform convergence with class 1 functions is what we're dealing with. When such a thing can be done, we get what we will call a convergence theorem. We're going to deal with 4 classes of functions. Class 1, class 2, class 3, and then the kind of the foundational class 0. I'd sort of berated those, belittled them by calling them class 0, but they were sort of a foundation. So we're going to see convergence theorems for each of class 1, class 2, and class 3. So they will be a linearity and monotonicity result for all 4 classes of functions, and a convergence theorem for the last 3, all but the 0, class 0, will have a convergence theorem. This next note shows that for the class 1 functions, we can't get away simply with pointwise convergence. We can do a little bit better than uniform convergence, but there's got to be some sort of uniformity that will pop up. But notice the following, and these functions are so elementary that this argument's valid to show that pointwise convergence doesn't work for the Riemann stuff either. Define f sub n on the interval 0, 1 to be f sub n is 0 if x is 0, or in the interval from 1 over n to 1, and define it to be n if x is in the interval from 0 to 1 over n. So here's a picture of what's going on. The aspect ratio here is all off. I've got the x-axis, the units are a lot longer than they are on the y-axis. So we can see what's going on. But here's f sub 1. So let's see, we get 0 at the endpoints and a value of 1 in between. And the area under this curve is 1. It's 1 by 1. So the aspect ratio doesn't show that. The area under it's 1. For f sub 2, we're going to have it take on the value 2 on the interval from 0 to a half and let it be 0 everywhere else. Well, now the area under it is still 1. It's 2 units high and a 1/2 unit wide. Area under it's 1. Go to 3. F sub 3, height of 3 on the interval from 0 to a third. Okay, it's getting narrower, but it's getting taller as well, and the area under this curve still remains 1. Usually describe this in terms of like when you, if you blow up a balloon, seal it off. Well, when you squeeze it in the middle, it squirts out on the side because the volume stays the same. Yeah, it's kind of the idea here. We're squishing this in on the sides, and as we do so, the top moves upwards and squirts upwards, if you will, in such a way that it maintains an area of 1 underneath. Well, what's the limit function? That'd just be the constant function 0. Now, you choose any number between 0 and 1, little number over here, really close to 0. Well, eventually, as n gets large enough, that sequence of functions will take on the value 0 and it'll stay 0. And that holds for any number between 0 and 1, strictly between 0 and 1. At 0 and 1, it's always 0. So the limit function is 0. But the area under each of these is 1. The area under this one's 0. That's a 0 function. All right, well, you better be careful taking limits in and inside and outside of integrals then. Because what we have is f sub n converges to the 0 function, does it pointwise. Shouldn't be controversial. It doesn't do it uniformly though. There's something about having these function values so far from their limiting value, and the way it's done violates uniform continuity. I leave it to you to convince yourself this is not uniform convergence. This is the kind of example you might see in senior analysis too. The integral of all the f sub n's is 1. Area under it's 1, 1, 1 for all n. So if we look at the limit as n approaches infinity of the integrals, They're all 1, so the limit's 1. But the integral of the limit function is a 0 function, and its integral is 0. We can do this with Lebesgue, written in Lebesgue notation. We could easily do this in Riemann, the Riemann setting as well. All these functions are Riemann integrable. We've just got a couple of points of discontinuity. These are Riemann integrable. And the integral of the limit is not the limit of the integrals. The limit of the integrals is 1, and the integral of the limit's 0, and 1 and 0 are different. So you can't always take limits in and out of integrals. Riemann or Lebesgue. So we want to establish our first convergence theorem. To do so, we're going to need Egorof's theorem, which will allow us to deal with a nearly uniform convergence. Egorof's theorem said, I'll repeat this because we'll need it in the proof of our convergence theorem, says, assume E has finite measure, let f sub n be a sequence of measurable functions on E that converges pointwise on E to real valued function f. So we got pointwise convergence of the sequence. The claim is, for every epsilon greater than 0, there's a closed set f, a subset of E, on which we have uniform convergence, and the measure of the difference can be made less than epsilon. In other words, we've got uniform convergence of that sequence of functions nearly everywhere. There's a little special word there. They threw out a closed set, not just any old set. Okay, Egorof's theorem then gives us that pointwise convergence in a setting of finite measure sets, which is where we are, is nearly uniform convergence. Pointwise convergence is nearly uniform convergence, a way to somewhat remember it. All right, so to deal with this example we saw previously, we need some kind of boundedness to be imposed. And what we'll impose is called uniform pointwise boundedness. Not uniform convergence, it's a boundedness condition that we're going to impose. Maybe ain't too much of a surprise because we're dealing in class 1 with functions that are bounded. All right, so our first convergence theorem is called the bounded convergence theorem because we're dealing with all this bounded stuff. Bounded functions on sets of finite measure, class 1 functions. We'll have 2 more convergence theorems for class 2 and class 3. Let f sub n be a sequence of measurable functions on a set of finite measure E. Suppose f sub n is uniformly pointwise bounded on E, that is, there's a number, capital M, greater than or equal to 0, for which f sub n, an absolute value, is less than or equal to capital M on set E for all n. So not only is every f sub n bounded, but all the f sub n's are bounded by the same number. That's the uniformness that they've snuck in. So uniformly pointwise bounded means there's a bound that holds for all of the f sub n's. So it'll hold for the limit function too. If, under those conditions, f sub n approaches f pointwise on E, then the limit of the integrals is the integral of the limit, the integral of the f function. The book leaves this intermediate stuff out when they state their convergence theorems, and that's just a shame. But you want to think, well, I took the limit inside the integration, right? The limit jumped inside. True, when it gets inside, it produces function f, because that's what we're dealing with here. But when you hear convergence theorem, think of it as limits go inside integrals. Let's prove that one, and that'll be it for this section. Okay, so uniform pointwise bounded, pointwise convergence gives us a convergence theorem. Okay, first function f is measurable. Pointwise limit of measurable functions is measurable, a measurable function. So f is measurable since it's a pointwise limits of the f sub n, since given there. F sub n is less than or equal to m for all x. So f of x, the limit function, is also less than or equal to m. As I said, it's got the same bound as all the f sub n's. So everything in sight is a bounded function on a set of finite measure. So we really are dealing with class 1 functions. For any measurable subset, A of E and any natural number n, we have the following. Let's take the integral over E of f sub n minus the integral over E of f. The difference of the integrals over the same set is the integral of the difference, linearity. A is a subset of E, so we're going to break this up. Remember we mentioned Egorof's theorem a while ago? So I'm going to break this up into two pieces. No constraints on set A just yet. We'll do this in a particular way shortly. So we can break this into an integral over A plus an integral over E set minus A. These are disjoint. Corollary 4.6 told us we could do that summing of integrals, that additivity type behavior, if you have disjoint sets, and A and the complement of A and E are certainly disjoint. Okay, so difference of the integrals can be written in this particular way here. All right. By theorem 4.5 and the two corollaries we had, so this is the stuff we know about class 1 functions so far. The linearity and monotonicity, along with, let's see, the addition over the sets we just used, and that thing with absolute values that we established as well. The absolute value of this difference, that is the absolute value of, here we've used the linearity, the integral of the difference, is less than or equal to the integral of the absolute value. Okay, that right there where the absolute values jumped on that integrand, that's corollary 4.7 that allows us to do that. Corollary 4.6 allows us to split things up, as we were just discussing, those with different functions. Okay. We know f sub n and f itself. Each of these are bounded by that constant m, so their difference is bounded by twice that constant m. So we're going to look at that as a bound on E set minus A. No constraints on set A just yet. No Egorof's theorem yet either. But I know M is a bound on the F sub n's and the F. So the difference, I mean, they could be up to 2 M units apart. Think of it like that. Bound means I might have close to positive M with this one and close to negative M with this one. So when I take the difference, I actually get them 2 M apart. But we get the bound as triangle inequality is what it is. A bound of 2 M there. This is a constant function, which is a simple function, I guess. And then we can write that, that integral simply as the constant times the measure of the set. We're integrating over E set minus A. So we can get the absolute value of the difference to be less than or equal to this, regardless of what set A is. Now, let's cleverly choose set A. So we can make both of these things small. I want the measure of E set minus A to be small, and I want this integral to be small somehow or other. Gee, if f sub n and f are close to each other throughout set A, that sounds like uniform convergence, we can make this small. So we're going to make both of these small, and here comes Egorof's theorem. Let epsilon be greater than 0. Since E has finite measure, that was required by Egorof's theorem, there's a measurable subset A of set E on which f sub n converges to f uniformly, and the measure of E set minus A can be made small, less than epsilon. Actually, let's make it less than epsilon over 4n, an arbitrary positive number. Okay, Egorof's theorem says you can get uniform convergence if you'll throw away a set of small measure. I choose that to be small. Why over 4m? We're going to replace that with a 4m. I'm sorry, an epsilon over 4m. We'll get some cancellations. This will give us epsilon half, and we'll get an epsilon half out of this also. So that's why we're choosing this. The uniform convergence on set A says I can make f sub n minus f an absolute value as small as I want throughout set A on set A by making n sufficiently large. Definition of uniform convergence. How little you want to make it? Let's make it epsilon over the measure of A. We'll do some monotonicity stuff, and there we'll go. So this also an epsilon over 2 related to what's going on here. Definition of uniform convergence. There's our arbitrarily small number. So when we take n sufficiently large, Then from equation 7, we get that inequality to be the function here is bounded by epsilon over 2 times the measure of a. So we can do some monotonicity stuff there if you like. And then having this bound over set A produces an upper bound of epsilon over 2 times the measure of A. We pick up the measure of the set. We have a similar result in calculus 1. As I said, I wanted to make the measure of E set minus A. We're going to make that less than epsilon over 4. So we'll replace that with an epsilon over 4 right here. We get cancellation there with an epsilon over 2. We'll get cancellation with a 2m and the 4m to produce another epsilon over 2. And there's your epsilon. We started up here for index n sufficiently large. We've got the absolute value of the difference less than epsilon. There it is right there. Absolute value of the difference less than epsilon for n sufficiently large. The sufficiently came out of Egorof's theorem somewhere. That means this sequence of numbers converges to this number. Definite integrals are just numbers. This stuff may look exotic, but as soon as you see the definite integrals, the things are just real numbers. For now, they might be infinity. They might be extended real numbers here one of these days. But right now, they're just numbers. And we got a sequence of real numbers that converges to this real number. Definition of convergence of a sequence. In other words, the limit of the integrals is the limit is the integral of the limit function. That is the integral of the f function. And that, kids, is a convergence theorem. All right, so that was a bunch of stuff, but that takes care of section 4.2, takes care of class 0 of functions, simple functions, and it takes care of class 1 of functions, bounded measurable functions on sets of finite measure. What we'll do next is non-negative functions. Okay, what could go wrong with non-negative functions? And the integrals might diverge to infinity, which is okay. And finally, in class 3 of functions, the next section will deal with functions that can be positive or negative, but we don't want to run into no infinity minus infinity indeterminate nonsense. So we'll have to deal with that. And the way we approach it, you can tell clearly that's what we're doing with the definitions we have. Thank you for your attention. Have a nice day, and we'll get into the next class of functions in the next section. I'll see you there. Bye-bye.